Hey guys, this video is for the students that can't make it to class for the review because they're leaving early. So anyway, I'm going to go through the Chapter 4 and Chapter 5 clickers, lecture clickers, and I'm going to go through them fairly quickly so I can fit it all into one video. So that means you're going to have to pause on the questions until you can think about it and come up with an answer, and then look at the answer and continue on. I will give brief explanations for ones that I think may be a little bit confusing, but for the most part, we'll just go right on through them. Okay, so here we go. Here's the first one. All right, and I'm going to reveal the answer right about now. Okay, so what you can see here is that the vertical components cancel, but there's more to the left than there is in the force. So that means there's a net force to the left, which means it will be pointing to the left as it says in the question. Okay, here we go to the next one. Ball rolling down a ramp. So you should pause it because I'm going to reveal this in right about now. Okay, so the idea here is that as soon as the ball leaves the ramp, it's in free fall. So the only force acting is the gravity pulling it down, which is the weight of the ball acting vertically down. It takes us to the next one. Steel beam hanging from a cable. And here's the answer right about now. So it's just a beam hanging from a cable. So it's the gravity pulling down, the beam pulling up, and it is in equilibrium. So they should be equal. Bobsledder pushing her sled. Bringing up the answer right about now. Okay, so all we have once she's in the sled is gravity pulling her down, the normal force keeping her from sinking to the center of the earth, and then the friction, which is slowing her down. Remember on all of these, inertia is not a force. So the fact that she jumped in and her inertia is now part of the sleds, that really doesn't matter. Once she's in it, it is what it is, and it's rolling along. This one is not in equilibrium because there is some friction, which isn't offset by a push, so she will slow down after a while. Number 5, cart being pulled to the right with a steady force. Here comes the answer right now. Constant acceleration because it's constant force. Next one, number 6. Constant force causes an object to accelerate. If we double the mass, what happens to the acceleration for the same force? Here's the answer now. Twice the mass, half the acceleration with the same force because it's a linear relationship. That's what it's showing. Here's the next one. Object push with a net force, and the answer is now. This one they changed 2 variables, so they did 4 times the mass and twice the force. So 4 times the mass would be 1/4 the acceleration, but twice the force will be double the acceleration. So you put those together, you wind up with half the acceleration, so it's 1 meter per second instead of 2. Here's the next one, number 8. Long train traveling pretty fast. Here's the answer right now. Now the skier has the greater net force because the train is in equilibrium. The skier is accelerating, so that means that there is a net force acting on the skier. Here's the next one. Object on a rope. Answer comes in now. All right, now again, this one is in equilibrium. It's descending at a constant speed, so it's not accelerating. That's equilibrium, so the forces have to be equal in all directions. So the rope tension equals the object's weight. Here's the next one. This time, hint, hint, it's not in equilibrium because it's decreasing speed. It's slowing down. So here comes the answer. So the tension has to be greater than the weight because the acceleration is upward. Another way to think about that is it's going down but slowing down, so it's descending at a decreasing rate. So not in equilibrium, net force is upward. Next question. Elevator lifted by a cable. All right, here's the answer right now. There it is. Okay, so what this shows is that the downward force is greater than the upward force. So it's moving upward, but it's slowing down. Since it's slowing down, the acceleration is downward, and that means there has to be a net force downward. So that's why the tension is less than the weight. Next one. Ball tossed straight up. Here comes the answer right now. Okay, once it leaves its hand, it's in free fall, so the only force acting is gravity, its weight, so there's only a vector down. Next one. Pendulum hang from the ceiling. Here comes the answer right now. All right, and this is the one. The downward vector is the weight on the ball. So the gravity is pulling the ball straight down. The other force acting is the tension in the string, which is going up that way. Now, as you can see, these forces are not in balance. There's going to be a net force kind of down and to the right, but that means that the pendulum is going to be accelerating down and to the right. So the force, the free body diagram does actually reveal what is happening in real life. Here's the next one. Car parked on a hill. The answer right about now, okay, it's this one. The weight always acts straight down. The normal force is always perpendicular to the surface, so that goes up and to the right. And since it's parked on the hill and not moving, that means that there has to be some friction going up the hill to keep it from sliding down the hill. Otherwise, the net force, like if it was option A over here, there'd be a net force going down the hill and the thing would be coasting down and accelerating. Here's the next one. Number 15, car being towed this time. All right, here comes the answer right now. It's D. The key thing here is constant speed. It's being towed, but it's in equilibrium, not accelerating, not speeding up, not slowing down. So the tension on the rope has to be matched by the friction and probably the air resistance if it's going at any significant speed. But all the forces have to be in balance so that it maintains constant speed. Okay, I think that's the last one. Nope, one more here. Let's go. Okay, here comes the answer right now. This is a third law problem, third law question. Action and reaction force, and I guarantee there will be one of these on the AP exam. They always make it look different, but it's always asked the force of one on the other and ask you the force of the other on the one. So this is it, equal to the force of Sarah on Jack. Equal in that magnitude, opposite in direction. 17, mosquito splats on a windshield. Find the correct answer, and the answer, well, the answer is right about now. There it is. Again, this is a third law, action-reaction. The mosquito pushes on the windshield with the same force that the windshield pushes on the mosquito. Now, the reason that the mosquito breaks and the windshield doesn't is because the windshield is stronger than the mosquito, but they do experience the same force. Think of this as if you had one of those 1-pound Hercules beetles, the largest flying insect in the world. If that hit your windshield and you're driving fast, it might break the windshield. It would break the beetle too, but the force is the same on both. It's just a question of the strength. Okay, and that's it. That's for that one. So let's escape out of this one and we'll come up with chapter 5. Here we go. I think we're doing all right on time. And we will go to a slideshow from the present. There we go. Here we go. So this is chapter 5 is the one where we apply Newton's laws. So we're looking at forces in different directions and adding up vectors and all that stuff. And here we go. We're adding up vectors on a ring that's hanging. So here's the answer right now. Here it is. So the force F is 20 times the sine of theta. And the reason is because if it was just one of these, it would be the vertical component of this force is 10 times the sine of theta. Sine theta is opposite over hypotenuse. So the vertical component of one of these is 10 times the sine of theta, but there's two of them, so we multiply it by 2, so 20 times the sine of theta. And there we go. Box sitting on the floor of an elevator. Here comes the answer right now. Okay. Now this is just a greater than less than, so you don't actually have to hang numbers on this, and AP exam likes these ones as well. All you have to know is that the normal force is greater than the weight, because there has to be enough normal force to not only keep the box from falling into the basement, but also to accelerate it upward. So the normal force has to be greater than the weight, mg. Here's the next one. Box being dragged along by a rope. And here comes the answer. All right, now the normal force is less than the weight, and the reason is because the rope is being pulled upward at some angle, which means there's an upward component to this tension, which is lifting the box off the ground. Another way to look, so therefore the normal force isn't equal to the weight. Another way to think about it is the box is partially hanging from the rope. So its entire weight is not being supported by the ground. And since normal force is a reaction force that only exists when something's pushing on the ground, then the normal force will be less. Here's the next one, number 4. This one is a little bit dense. You can puzzle your way through it and see it, but it's just an application of SOHCAHTOA. That's the answer. You can puzzle it out. Here's the next one. 50-kilogram student standing in an elevator. Okay, when the elevator accelerates upward, the scale has the scale and the floor has to support the student's weight plus enough extra force to accelerate him upward. So the scale is going to show more because the scale does kind of show the normal force. Next one. Here's the answer right about now. Okay, the explanation there is a good one. If the elevator and the student are falling, there's no apparent weight. It's like an astronaut in the space station. Box being pulled across a rough surface. That implies that there's friction. Okay, so the force is equal to the tension. And I think that's Newton's third law rather than Newton's first law, but we'll go with it. Anyway, whatever the tension is, the friction has to balance it because it's in equilibrium. Okay, next one here. So for this one, you're going to have to actually do the calculation or do a rough estimate of the calculation using the coefficient of friction and the weight of the box, etc. Here's the answer right about now. And it works out that there's not enough tension to get it going. The friction is around 40 newtons. Here's the next one. All right, and the answer comes in now. So when the rope breaks, now there's no more force on the box. So first law takes over and its inertia is all that's carrying it along. And since there is friction, that's going to be a constant force working against it, which will accelerate it backwards, which means it will slow down until it stops. But it will be a constant acceleration. That's why they say steadily. Next one. A couple things hanging over a pulley. Answers showing right now. There it is. The explanation is very good on this one. This is sort of like the scale in the middle of the table with the pulleys going over each side. It's the same idea. Here's the next one. Okay, don't be put off by the complexity of this diagram. It's just asking about action-reaction pairs. So think this one through. Look at the options and see what they're saying on the diagram. And here's the answer right about now. There it is. So normal force of A due to B and the weight of A. So the weight of A is pushing down on B and the normal force is pushing back. And the other ones generally are disqualified because they're more than two objects. That's usually the problem. Okay, and it is probably worth your while to go through these and figure out why the incorrect answers are incorrect. It's that 4-part test of what the third law is. Okay, A and B. Okay, this one may take some head scratching, but here comes the answer right about now. Okay, so the tension in 1 has to be less than the tension in 2. There's a couple ways to look at this. One is to think of this, let's see, where's my arrow? There it is. You can think of this as kind of a train, and this rope is pulling the entire train, so there's a lot of tension in it. This rope is only pulling the back part of the train, so there's less tension in it. That's one valid way to look at it. Another way to look at it is to know that B is accelerating. And for B to accelerate, there has to be a net force going forward. So that means that the tension in the front one has to be greater than the tension in the back one, so that there is a net force forward and B can accelerate. Either one of those interpretations will get you where you need to be. Okay. Next one. Here's a hand slowing stuff down on a frictionless surface. Here's the answer right about now. There it is. Okay, and it's kind of the same idea as the last one, except that it's compressions, it's pushing rather than tension pulling. The B is being slowed down, so there has to be more force pushing on the front than pushing on the back. So if there's a net backward force, which it will decelerate the box. Here's the next one. This is the scale hanging over the table, so hopefully you'll get this one right. There it is, 5 kilograms, as promised. Next one. Weight being dragged down a table. This is similar to what you did in the verifying Newton lab, but this time it's a frictionless table. Okay? We want to know the tension in the string. Here's the answer right now. There it is. Okay, and the tension in the string has to be less than the weight, or else the weight won't descend, won't accelerate downward. So that was the last one. Okay, very good. I hope these were helpful to you. Those of you who are taking the test on Monday, we'll see you Monday, and good luck to you. I'm sure it will go fine.